All right, part two. Here we go. Albert Einstein noticed some oddities. So, I don't know how to spell that. Oddities. All right. The oddities I wrote on the back of your paper. Brian, could you read number 1 on the back? That one I understand.
Electrons were ejected within a few billionths of a second after the light was turned on.
All right. So it turns out what they're talking about, draw somewhere, I didn't give you much room, draw a piece of metal, and the light is coming as a wave will say, and it's hitting the metal, and after a while, since the waves are moving, they have energy, kinetic energy, anything that moves does. So after a while, there will be so much energy from the wave hitting the metal that it will spew off some electrons. So these are not drawn to scale. You can't see electrons, but you can draw a couple electrons coming off of the metal. That is called the photoelectric effect. And I wouldn't even bring it up if it didn't create a whole storm of ideas. Photoelectric effect. When light hits metal, electrons will spew off from it. They fly off, and then those are called photoelectrons. So, it makes sense. But, it turns out, again, the oddity that Brian read, it said that they flew off how quick, Brian?
A few billionths of a second.
A few billionths of a second. So when we got to the point we could measure such things, we realized that if light was a wave, it would take some time for that metal to actually absorb enough energy from the light to throw off the photoelectrons. So it shouldn't go off that fast. It's basically instantaneous, a few billionths of a second. So that was an oddity. If light was a wave, and you can write that near number 1 or put an arrow and say, if light was a wave, if it was really a wave like we thought, if light was really a wave, the electrons should take longer to fly off. Waves do carry energy, but it takes time for the metal to absorb that energy and the electrons to obtain the energy to fly off, and they flew off almost instantaneously. So that was an oddity if light was really a wave. Now the other 3 oddities are harder to understand and explain, but I'll give you a general idea. But since I don't understand them, it's going to be hard. So would you read the second one, MM?
The intensity of the light had no effect on the energy of the electrons after they left the metal. The more intense the light, the greater number of electrons, but the energy of the electrons was independent of the light.
Alright, so this was the second oddity that Einstein presented. And basically, he was saying that the intensity, I erased it, but remember intensity had to do with amplitude. It had no difference on the energy level of the electrons that flew off. So they should have had more energy if light was a wave. So we can say that. And again, this is not what we're studying. We're not studying these oddities, but we want to know that they exist. So for this was number 1. Number 2, the electrons that flew off. The electrons that flew off should have had more energy if light was a wave. I can't really explain that one. All right. After you write that down, would you read number 3, Alex?
Okay. Each metal had a unique cutoff frequency. So light used is below this frequency, electrons would not be emitted.
Okay, so we've already seen on the front of our paper that light has different frequencies, different colors, and then it actually goes below and above the visible light spectrum. So when are you finished writing that, MK, look on the front and tell me what kind of light is below and above visible light. So you read that other chart there. So go below first. What goes below visible light and frequency?
Below would be ultraviolet.
Ultraviolet. What else? Keep going.
X-rays.
And okay, and then what's above?
Infrared, microwave, radar, TV, FM, radio.
Isn't it kind of funny that radio is a light wave? Doesn't think it would be a sound wave? It is not. So you learn something every day in this class. So, all right. So on that one, the one that Alex read, it said that as a certain frequency, when it reaches a certain frequency, the light that you would shine on the metal, if it was a low frequency and below a certain level, no more electrons would fly off. But if light was a wave, and even if the frequency was lower, eventually, if the light shined on it continually, it would absorb enough energy to fly off, but they did not. So I'm not going to have you write all that. So number 3 was also an oddity. If light was a wave, that should not have happened. All right, Zach, number 4.
The maximum kinetic energy of the emitted electrons was directly proportional to the frequency of the light used.
All right, and it should have been, if it was a wave, it should have been proportional to the frequency, not the intensity. So we don't have to write that one either. I just want you to know that he observed 4 major oddities, and all of them indicated that light was not a wave. So Einstein threw this fly into the ointment. Light is not a wave. It is, all of these oddities can be explained if it is a particle. So he said the particles are called photons. They're little bundles of energy. That's what's oscillating toward us, and they explain those 4 oddities. However, if light is a particle, this wouldn't happen. So, is light a particle, or is it a wave? So Einstein, he had like a large percentage of his brain working that we don't, and he said that he's willing to accept the fact that sometimes light acts like a wave, and sometimes light acts like a particle. We actually call that the wave/particle duality of light. So somewhere on the paper, this is the star idea, and that means wave. Like he said, light acts like a wave sometimes and like a particle other times. We can't really understand it. Sort of like we know the guy yesterday in the video went to the beach and asked everyone, "What's light?" They're like, "Oh, it's color, it's aura, it's there isn't a real good idea. We don't have a better answer than the people on the beach, really." So write this down and star it. The wave-particle duality of light. And that means it could be either and acts like either, depending on the circumstance. So, all right, let me give you an equation that will exercise the fact that this is Einstein's equation, that it's a particle. And we're going to add it to our list. It is E equals H F. And when I look at that from a distance, I see